let's identify the torque due to each of the forces in our picture. So we'll have a torque due to the tension of the tape, the tension in the cable. We'll have a torque due to the force of the sign on the right. We'll have a torque due to the force of the sign on the left. We'll have the torque due to the weight of the post, and we'll have the torque due to the weight of the bolt, due to the force of the bolt. So we'll do our torque table. We want to get our signs. Okay, we'll care what method will we use to do the torques. This time let's use lever arm, let's use moment arm. So torque is our perpendicular, which is our moment arm, times our force. And if we're going to do a torque problem, we need to identify the pivot. Let's put the pivot right there on top of the bolt force. So let's put our pivot right here. So let's start going through it. So the tension in the cable will tend to turn the post counterclockwise, so that's going to be a positive torque. The next line in our table will be what is the moment arm, what is the R perpendicular. Let's just do another drawing over here so we don't clutter up this one too much. So here's our post, here's our pivot, here's our tension force at some angle. If we want to draw R perpendicular, if we want to draw the moment arm, it has to connect this pivot to this line of action. So by line of action means we extend the line of the force. We make it as long as we wish. So there's our tension. Now we have to connect the pivot to this line, and it has to connect at a right angle. So to make it a right angle, it has to connect this way. So here is our moment arm right here. So let's think about how are we going to be able to find this. This is the length of the post. It's 1 meter long. I'm just going to call it L right here. We'll put in numbers afterwards. The tension force is at some angle theta, which we are going to be able to figure out from the geometry. But let's just look at our R perpendicular for right now. R perpendicular is opposite our angle. This is our hypotenuse. This is the opposite. So R perpendicular is going to be L times sine theta. So there's our moment arm for the tension force. So we'll also fill in our forces next. The force due to the tension is the tension. Then we'll fill in what is our torque value. So our torque is going to be plus L times sine theta times the tension T. Okay, next let's do the torque due to the force of the sign on the right. We ask, what does that force do? That tends to turn it down this way. That's a clockwise rotation, so that would be a negative torque. What is the R perpendicular for that one? Let's just draw our post again. Here's our pivot. There's the force due to the sign on the right. R perpendicular connects this pivot to this force at a right angle. So to do that, we just go straight across. There's R perpendicular for this guy. That distance is given in the picture. It's 80 centimeters. So 0.80 meters. The force is the force of the sign on the right, which is a half the weight of the sign, so mass of the sign times g over 2. So our torque is minus 0.80 meters times the mass of the sign times gravity divided by 2. Torque due to the sign on the left will also turn it clockwise. It's a negative torque. Let's see, we can draw that R perpendicular, although we probably get the idea of how this is going to look. There's the force due to the sign on the left. R perpendicular connects the pivot to that at a right angle, so it's from the pivot to that force. That's given us 60 centimeters in the diagram, 0.60 meters. That force is half the weight of the sign, so mass of the sign times gravity over 2, so our torque is minus 0.60 meters times the mass of the sign times gravity divided by 2. Then the torque due to the weight of the post, let's draw that one in too since we have just enough room. There's the pivot, there's the weight of the post itself. So our moment arm or the lever arm connects the pivot to the force at a right angle. So there's our R perpendicular. We know we draw this in the middle, so it's a half the length of the post. The post is 1 meter long, so half the length is 0.50 meters. The sign of the torque, this force will turn it, oh gee, come right off the screen. This force will turn it clockwise, so that would be a negative torque. And the weight is going to be mass of the post times g. So then the torque will be minus 0.50 meters times the mass of the post times g. The torque due to the bolt is not going to turn it at all. If we have our force here and we push at the pivot, it doesn't turn. So there is no sign. The R perpendicular is the distance between the pivot and the force. That's going to be 0. The force is going to be the force of the bolt, and then the torque is those three things multiplied, so that torque is going to be 0. So then torque due to the tension, the moment arm goes from the pivot to the force. We see that that's opposite that angle theta, so we use sine, L sine theta times T. For the force of the sign on the right, that points straight down. Our moment arm goes from the pivot to the force, has to meet at a right angle. So since this is already perpendicular to the post, the moment arm is just along the post. And the distance we can see from the diagram, given at 80 centimeters. Similar for the force of the sign on the left, points straight down, so the moment arm comes across, so it's along the post because those are already perpendicular. The diagram gives that at 60 centimeters. And then the weight of the post, that's drawn right from the center, so the moment arm is from the pivot to the center, so that's 1 meter long. So that gives us our expressions for our torques. To solve the problem, to find the tension and the forces, we're going to apply the conditions for static equilibrium. That the sum of the torques is 0, sum of the forces in each direction is 0. We'll apply those, and that'll let us find those forces. We'll do that part next.